Good morning. It's a great honour to be with you in your homes here at Game 2020. My name's Simon West. I come from the Gun Trade Association and I've been asked to speak to you today about shotguns and ballistics. I have a little bit of professional background in ballistics, but mostly for artillery systems. The interesting thing is probably shotguns have as much complexity as an artillery system. So there's still a lot to learn, but let's have a chat through some of the issues that might affect how you choose to shoot in the field. Now we have a gun system that includes the shooter, the gun, the ammunition, and all the components within it. And at times of change, like muzzle loading to breech loading, black powder to nitro propellants, and today's transition towards lead alternatives, we see the need to compensate within the system for that change. All the time, however, we should remember that the current system has evolved over hundreds of years to do the job it does, relying on lead. So we have quite a challenge ahead of us. Ballistics breaks down into internal, external and terminal ballistics. This covers what's happening in the gun, what's happening in flight, and what happens when the projectile hits the target. Now the gun is just a machine. It converts propellant energy into kinetic energy of the projectile, which then transfers energy into the target to produce a humane kill. Now, from our physics, we know that kinetic energy is a function of both mass and velocity. Mass is a combination, in turn, of the density of the material and the size of the projectile. Now, as we change a substance within the projectile and you change its density, we need to look at ways of compensating either for size of projectile or the velocity of the projectile. And that's what the ammunition makers are looking to do. So let's look at those alternatives. What we know we're looking for is something which is dense to be able to help carry that energy, cost effective, and we need to avoid the toxic and radioactive parts of the periodic table. Now, right next to lead is the element bismuth. This has very similar physical properties to lead, but is a degree more pricey. It's slightly less dense, so we would look to use one shot size larger. Next, a very good candidate in terms of density is tungsten, but it's very expensive and very hard on its own. So the manufacturers have looked at creating a tungsten matrix, which you may see for sale, and that is tungsten powder mixed with a polymer and then compressed into small pellets. And then finally, steel shot, or in fact what is soft iron. It's closer to the elemental state of iron. This is a fair bit less dense than lead, is somewhat hard, but it's cheap. Now the hardness means we need to protect it from the steel walls of the barrel, and that means that the regulations state that that shot should be contained in a cup. Now, because it's lighter, we tend to go 2 sizes larger to ensure that we get comparable weight and therefore effect at the different ranges to the target. Internal ballistics. The propellant is going to be ignited by the primer and fire the wad and projectiles up the barrel. Now at this stage, the most important thing for us to identify in terms of safe use is that our cartridges are going to fit effectively into the chamber. Now, as you can see, there is a gap here between the end of the rolled or crimped cartridge and the end of the chamber. Now, that is essential. It is essential because when this crimp opens, it will fill that space. And we've got to have an unobstructive route for the wad and projectiles to exit the chamber. So reading the proof marks on your gun and knowing the chamber length is absolutely critical to ensure that you buy safe ammunition for your gun. We'll look more at that in a bit. Now, assuming a safe cartridge has been loaded and the trigger has been pulled, the propellant is burning and pushing the wad and projectiles up the barrel. Now, this will create an equal and opposite reaction, as Newton told us, and provide us with recoil, and indeed forces that will try and open the breech end. And that's why that's part of the proof test, to ensure that the action is tight and safe. Now, the shots themselves are being accelerated at a very high speed. And what happens in the case of lead is that those shot settle and press against each other and do deform slightly. Now, lead has that ability. Steel does not accept deformation, so it will create a lot of pressure outwards onto the barrel wall, and that's why steel shot is contained in a strong plastic or fibre cup to protect the barrels from that abrasion. Now, in their ballistic journey, the shot next face the choke. Now, in the 1860s, Mr. Greener and Mr. Pape were developing ways of increasing the effectiveness of lead shot, and identified that constrictions at the end of the barrel would tighten up the pattern of the shot in flight and at the target. By the time the shot reaches the choke, it's approaching 900 miles an hour, and it's accelerated to that speed over just 2 feet. So any small constriction in the barrel is likely to experience quite a lot of force from the projectile coming up. Now, lead has a degree of what I would call squidgeability. Now, squidgeability really takes two forms. First of all, the pellets themselves, as they're being squeezed, are able to reposition themselves into the slimmer form to get through the choke. Secondly, as you can see in the lead pellets here, they can suffer deformation, which allows them to pack more tightly amongst each other. On this side, you can see steel pellets of two sizes larger that experience almost no deformation at all. And it's that lack of deformation that produces the potential stress on a tight-necked choke, which is why for a standard steel cartridge, the proof authorities recommend half choke or less, really to alleviate that pressure of the shot at the choke neck. What we have here is a diagram to show the different levels of choke getting ever more constricting across the bottom, and the tighter pattern of lead shot at different ranges. Now, lead shot experiences that deformation as it gets set back in the breech and squeezed in the choke, and as a result those deformed pellets fly less well, and they are the ones that will fly off to a flank because of the effect of moving through the air. The steel shot that doesn't experience the deformation and is more perfectly spherical are less likely to experience that sideways effect as they're in flight. So in fact, steel shot requires less choke. So not only are we saying it can't have much choke because of the lack of deformation at the choke neck, we're also saying it doesn't need it. So a quarter, half choke will probably be sufficient to give you the same sort of effect for steel as you previously had for lead. And now finally, terminal ballistics and target effectiveness. Now, there are two factors that we need to take into account here. First is the likelihood of getting sufficient pellets into the target, and secondly, ensuring that they've got enough energy to penetrate and hit vital organs. Now, Gough Thomas, well known to GWCT and the Game Conservancy in the past, set up a formula to help us understand this, and you can see that in the box bottom left. So for example, to produce a lethal kill on a pheasant, we would look to have at least 4 pellets with a striking energy with at least 1 foot-pound. And that's something we can calculate through our knowledge of ballistics to ensure that we deliver sufficient energy to the target. The second part of that, of course, is the probability. And not only have we got to have enough energy, we've got to have enough pellets covering the target. And we can look at that by patterning our guns with different types of ammunition to ensure that we get that maximum or the maximum effect by a minimum number of pellets in the 30-inch circle. And Gough Thomas would advise us that we need 120 pellets to achieve that coverage. So as we look at different alternative shot, we've got to look at both the energy they have to hit the target and maintain the right number of pellets to provide a proper coverage of the target area. So we've looked at all the factors relating to what ammunition does on its way up the barrel and on its way to the target. What we now need to look at is our own guns to understand what it is that we might be able to fire in each one. Now, guns are tested before they are sold after manufacture and any time during their life. They have to be in proof. And there are various levels of proof. The old ones would just been tested to black powder levels, and most of those are now obsolete, and whatever you do, don't use nitro cartridges in those. Your standard gun proof will be a nitro proof, and we'll look in a minute at the markings for that. But they are really designed for your standard cartridges, and also, as long as they're in good order, will be usable with standard steel cartridges. There was then a higher level of proof for magnum loads called superior, and then for steel, high performance loads, and those are higher velocities and higher momentum, there is a separate proof mark. Now, fundamental to all of that is that you must have the right size cartridge for your chamber. And you must never use a more powerful cartridge than the ones that your proof marks indicate. So it's then a matter of reading the proof marks on your gun. And the key things you're looking for are the nitro proof marks. And in this gun, you can see here, there is an NP with an armoured gloved hand with a scimitar. That's the London proof mark for nitro proof. Now, interestingly, you can also see nitro proof stamp there, and an older stamp, a Birmingham nitro proof mark is on there as well. Now, that curly R on the right hand side under a crown, that tells us that it was reproofed in London. So the reproof we're looking for is the nitro-proof size. Now the 0.729 inch that you can see marked up here indicates the measurement of a 12-bore gun, and it's against that that the gun maker or your dealer will check the bore size to ensure that it's still in proof. But what I want you to be most aware of is the 2.5 inch. That tells us that we can only use 65 or 67mm cartridges in that gun. Anything longer stands the chance of the crimp obstructing the wad and shot as it goes up the barrel and creating unacceptable pressures. This is a more modern gun with a metric mark telling us that it's 12 bore and a 76mm cartridge length. That's a 3-inch case. It's got superior proof, and critically it has the fleur-de-lis mark, which means that it has steel proof, meaning that you can fire high performance steel through that barrel. If you do not see that fleur-de-lis on your gun, you must only use standard steel cartridges. Now there are various publications from both the GTA and the Trust to remind you of these details later, but just a final reminder, cartridge size suitability is critical, and here are the chamber size equivalents across the different proof marks for different ages. Remember, never use a size too large, even if it appears to fit, because it does need that extra space for the crimp to open. So if you've got a nitro-proof gun with 2.5 inch chambers, of course you can fire lead, bismuth, tungsten matrix, and just coming to market now are the first 2.5 inch cartridges in standard steel. It's unlikely you'll be able to find them easily, but they do now exist, and we need to start testing them to see how effective they are at different ranges. If you have the benefit of 2 3/4 inch chambers, of course you've got everything at 65 and 67, but 70mm cartridges as well. And there's a very much wider choice of all of the different ammunition types at 2 3/4. If you have a superior mark, you can fire magnums, but only standard steel. It's when you've got the fleur-de-lis on your gun, then you can fire all of the others and the high-performance steel cartridges. So this is a 19th century Henry Holland hammer gun in 12 bore for 2.5 inch chambers. I've got an Ely number 4 Pro Eco Wad steel, and we'll see what it does. So the results. Well, alongside the test, I'd calculated that each of those number 4 shot had about 2 foot-pounds of hitting energy. So that's enough for Gough Thomas's calculations. He also suggested we needed 120 pellets in the circle. Well, on that shot, I got 113, but as you can see to the right, I wasn't exactly central. So I think we're pretty well at the stage where I've got a steel cartridge with sufficient energy and the right pattern to be able to field test. So now over to you. First of all, check your gun and find out what ammunition choices are available to you. Now, There may be some calibers and some chamber sizes for which there are no immediate solutions. There's plenty of research and development going on, and more will come to market over the coming years. For some calibers, there may not be a cost-effective steel solution, so it's either lead or bismuth for the foreseeable future. You might want to adapt your gun to give you more choice. Taking out choke and increasing chamber sizes might be an option. And of course there are new guns. Buy a few boxes of ammunition to start with, get onto the pattern board, and then once you've got your confidence, go out and field test. And finally, it's worth us realising that many of us are old traditionalists and we like using our old guns, but retrofitting modern ammunition to old guns is possible, but you may not get the peak performance that you desire. And then it's a matter of using your old gun on certain days and investing in a new gun to take advantage of the new innovation that's available through the different types of ammunition.